Okay, so let me see if this is okay. Let me this. All right, so we have pretty much covered most of chapter 6. So I anticipate we should be able to finish it today. If not, then we will have done most of that chapter. So what we're going to talk about now is a very important law when it comes to thermochemistry, and that is Hess's law of constant summation. All right. Now, in practice, there are certain reactions that are very difficult, if not impossible, to perform. All right. So, therefore, if you want to find the enthalpy change of that reaction experimentally, that would be a huge task. All right. So, an example of such a reaction would be the reaction between carbon and oxygen to form carbon monoxide. In practice, this is difficult. Why? Because it's very difficult to stop the reaction at the carbon monoxide because carbon monoxide will itself react with another half molecule of oxygen to form carbon dioxide. So basically, you're going to have, let me show you here. After the carbon monoxide, oops. After the carbon monoxide is formed, then what would happen is that the carbon monoxide gas will react with half mole of oxygen gas to form carbon dioxide, right? So it's very difficult to basically just stop there and do your measurements and all that, right? So very difficult in practice, if not impossible, all right? So clear this. All right, so basically, we can determine the enthalpy changes of such reactions if we know what the enthalpy changes of other related reactions um, are. And that's because enthalpy change is, as we said before, a state function. A state function that basically does not depend on the pathway to get to a particular enthalpy value, right? So as stated here, the enthalpy change of a reaction is the same whether or not the reaction is carried out in one step or through several steps, right? So that brings us now to Hess's law. And what Hess's law says is that if you have an equation that can be expressed or is the result of adding two or more equations together, then the sum of the enthalpy changes of those equations would be equal to the sum of would be equal to the enthalpy change of the first equation. All right, that's Hess's law in a nutshell. All right. So just to give an example, going back to the reaction that we just looked at, the reaction between carbon and oxygen, as we said before, it's very difficult to determine the enthalpy change going from carbon and oxygen to just carbon monoxide, right? Because if there are more oxygen present, then the carbon monoxide will react itself to form carbon dioxide, right? So it's very difficult to measure this enthalpy change. However, we know the enthalpy change total going from carbon and oxygen directly to carbon dioxide, and we know also the enthalpy change of going from carbon monoxide to carbon dioxide, right? So therefore, based on Hess's law, we can say that the enthalpy change here for the reaction producing carbon monoxide would be added to this value here, which is the value of going from CO to CO2. That sum would be equal to the enthalpy change going directly from carbon to carbon dioxide. And this value is known, can be measured experimentally, and this value is known as well. So therefore, we can, based on the fact that this plus this gives you this, we know that delta HA would be the difference between this value here and this value, all right? So basically, by subtracting this value from this value, you're going to get delta HA, which is the enthalpy change of the reaction going from carbon to carbon monoxide, right? So let me just show you another way of expressing what I've just described right here. So let me, I was doing something earlier. Okay, so um, so as I was saying before, well, before I even go to that, let me just use a hypothetical example, and then I'm going to apply this to the reaction with carbon and oxygen. So basically what Hess's law is saying is that if you're going from A to C, right? And let's say the enthalpy change for that is delta H3, right? But you can also go from A to C through an intermediate B, in which case the enthalpy change here is delta H1, and the enthalpy change here is delta H2. So what Hess's law is saying is that it doesn't matter if you're going directly from A to C, or if you're going from A through B to C, the total enthalpy change would be the same, right? So therefore, we can write down a relationship between delta H3, delta H1, and delta H2, and that would be delta H3 would be equal to delta H2 plus delta H1. All right? So that's basically what Hess's law is saying. Another way of expressing this, if I were to write down A going to B, and the delta H1 value would be associated with that reaction, and then B going to C, and that will have the delta H2 value associated with that reaction, then what we can do is add these two equations together to get going from A to C directly, and the corresponding delta H value, which would be delta H3, would be the sum of delta H1 and delta H2. And you see we get the same thing. So I'm just using two different approaches, this one or this one. The result will be the same, all right? So that's basically what Hess's law is saying. Now, applying this directly to the example that we just showed you, we can go from carbon to carbon dioxide directly. Of course, you have to add oxygen in there. Or you can go from carbon to carbon monoxide. So I'm just going to call this delta H3, even though the values were given. To go from carbon to carbon monoxide, you're going to add half a molecule of O2, and that will be delta H2. I'm sorry, delta H1. And then going from carbon monoxide to carbon dioxide, that will be another half mole of O2, and the delta H value for that would be 2. And again, we can write down the relationship between delta H3 and delta H2 and delta H1. Delta H3 will be equal to delta H1 plus delta H2, just like we did before. And in this particular case, based on the example that we just saw, what we're trying to find is delta H1, right? Because if you look at the example that we looked at, we know what delta H3 is and delta H2 is. So therefore, we can say that delta H1 would be equal to delta H3 minus delta H2. All right? So this is basically the utility of the Hess's law, which helps you determine the enthalpy change of a particular reaction if you know what the enthalpy changes of other related reactions are. All right? Yet, another way of doing it, just like I showed you up here, C plus half O2 to give CO, that's delta H1, CO plus half O2, and the enthalpy change for that is delta H2. So therefore, if you add, oh, by the way, CO2 would be the product here. And when you add these two, the carbon monoxide will cancel out. Half plus half gives you 1. So C plus O2 to give you CO2. The delta H value for that, I'm going to call that delta H3. And again, you see that when you add these two, delta H1 plus delta H2 gives you delta H3. That would be basically, again, the same expression right here. All right? Again, another demonstration of Hess's law. All right? Okay, any questions about this so far? Any questions? Okay, so problems involving Hess's law are a bit more complex, such as this one right here, all right? So this question says, calculate the enthalpy change of reaction A, and it gives you reaction A, given the data in the equations B, C, and D. So they gave you these three equations and their corresponding delta H values. And based on these three equations, you are to determine the enthalpy change for this reaction right here, all right? So what I'm going to do is copy and paste, of course, because I'm going to need space to do all this. And I'm going to paste it onto Word. First, I'm going to get rid of all this here. Okay, and then okay, so this is the question right here, all right? So we want to find the delta H value for the first equation here, and they gave you the three equations and their corresponding delta H values, all right? So what I would do is compare each of these equations to the first equation, right? And make some modifications based on that. So let's start off with this equation right here, right? If you compare this equation to the first equation, you'll notice that you have carbon on the same side of the equation, but you have a coefficient of 2 here, right? So what I would do to this equation here is to get a coefficient of 2 here. That means I'd have to multiply the entire equation by 2. If I do that, that means I have to multiply the enthalpy value here by 2 as well. So when I do that, I'm going to end up with 2 carbon solid plus, and by the way, when you're doing these questions, you have to include the state symbols, right? Because in some cases, the state symbols or the states of the different substances might change. You might have something where you're given a question where you're given an equation where, let's say you have H2O solid going to H2O liquid, right? So you have to be careful about use of the state symbols. Anyway, so in this case here, we're multiplying the entire equation by 2. So on the right side of the equation, you're going to have 2 CO2 gas, and the corresponding, excuse me, delta H value will be equal to, excuse me, 2 times minus 393.5 kilojoules, all right? Because you multiply everything by 2, all right? So that's the changes that we'll make for equation labeled B. Now, when it comes to C, again, we make the comparison between C and the first equation, and we notice that there is C2H4 here on the left side, but in the equation for which you're trying to find delta H, C2H4 is on the right side. So what that means is that for this equation, we have to flip it, right? So this one we multiply by 2, but this one we have to flip. We have to flip this equation so the reactants become the products and vice versa. So you're going to end up with 2 CO2 gas plus 2 H2O liquid. And then on the right side, you're going to have C2H4 gas plus 3 O2 gas. And what do you think happens to the delta H value when you flip the equation? If you flip the equation, if the reactants becomes the products and the products becomes the reactants, what is the effect it would have on the delta H value?
The sign change.
The sign will change. So therefore, whereas you have negative 1410.9 here you're going to have plus 1410.9 kilojoules. All right? Okay, very good. And then we get to the third equation. Now, again, we're going to compare the third equation to the first one. And what do we notice? We notice that we have one H2 here, but we have a coefficient of 2 in front of the H2 in the first equation. So what do you think we need to do to this equation? If we have only one here as a coefficient, but in this equation for which we're trying to find delta H, we have a 2 here. So what do you think we need to do to this equation here? How do you propose we get a 2 here, in other words?
A 2 on the H2 or the O2?
I'm sorry?
A 2 on the O2 or the C?
I don't understand what.
I'm asking which.
Oh, yeah, it's no question.
Oh, well, it would be the same coefficient either way. Yeah, so just multiply by 2.
Multiply the entire equation by 2, exactly. So when you do that, let me put here multiply by 2. So when you multiply this equation by 2, you're going to end up with 2 H2 gas plus O2 gas, because 2 times half gives you 1. And then on the product side, you're going to have 2 H2O liquid. So as a result of multiplying the entire equation by 2, what do you think happens to the delta H value here?
Multiply by 2.
Multiply by 2. So you're going to end up with 2 times minus 285.8 kilojoules. All right? So what we're going to do next is add up these equations together. And remember, when you have several equations that you have to add up, you cancel items that are common to both sides, right? In this particular case, that means that these 2 CO2 gases will cancel out here. These two H2O liquids will cancel out here. What else? So that's pretty much it as far as cancellation. Oh, wait a minute. No. This one is tricky. You have 2 plus 1 oxygen here. So that's 3 oxygen molecules on this side, which will cancel out with those 3 there. All right, everybody see that? So I think that's it. I don't think there's anything else left to cancel out. So we simply write down what is left. 2C solid plus 2H2 gas to give C2H4 gas. And this is the same equation as the first equation for which you're trying to find delta H, right? So the question is, how do we find delta H? And the answer is what? How do we find delta H for this final equation?
Do we add the 3 delta H?
We add up all these delta H values that we have here. All right? So let me get my calculator. So you're going to add 2 times 393.5. That gives you 70. Let me just put that here. That gives you 787, I'm sorry, 0.0 kilojoules. And then we have that. Oh, let me work out this here. 2 times minus 285.8, and I got 571. So this here, I'm just going to squeeze it here. This will be equal to, let me put it down here. This will be equal to 571 minus, very important, minus 571.6 kilojoules. So what I'm going to do now is add this to this to this, and that would be the delta H down here. So the delta H here for this reaction, I'm going to add, this should be negative as well. Okay, so I'm going to add 787.0, and that should be negative, plus 141.0.9 minus 571.6. And the answer I got is, and please correct me if I'm wrong, but I got 52.3 kilojoules. And that's basically how that is done. All right? Okay, any questions about this particular example? Yes, ma'am.
Up to 52.4.
Nope. No, well, let me do it again. I don't think so, but 787 minus plus 141.0.9, and then I'm going to subtract from that 571.6. Nope, I got 52.3. So I don't know, unless anybody else has a different result. But that's what I got. All right. Okay, any questions about this? Any other questions about this? Any other questions? All right, so going back to the PowerPoint. In fact, you know what? Let me go to the assignment, because there are some questions in that. Okay, let me go here. Let me go here. Okay, assignment. Come on. Assignment number 6. And download that. Scroll down. Okay. No, not that one. This one. Okay, so this one is another typical. In fact, I can guarantee your next test, well, not the next test, but test number 3, you're going to get at least one question of this type. All right. So it would be worthwhile for you to understand how to do these. All right. So let me hear what you have to say about this, because this is the approach that you're going to take is going to be similar to what we just discussed in the previous problem, right? So in this question, they gave you the equation for which you're trying to find delta H, right? And then they gave you these three equations and their corresponding delta H values. Okay, so let me hear what you have to say about this one. What would be your very first step using what we did before as a guide? What would be your very first step? Let me give you a hint.
Oh, okay, balance that. So multiply the second equation by 2.
You're partially right, but you need to do something else. Or not something else, something in addition, I should say. You're right about multiplying right through by 2.
Oh, so you'd have to multiply the delta H value well by 2.
Well, that too, but okay, that's true too. But here's one more thing that you need to do. Oh, somebody's speaking up online. Let me see here. Maybe this person knows what.
Yeah.
Flip it. Exactly. Thank you, Miss Anwar, Miss Afro Anwar. So there are two things you need to do to that equation. You need to, as you just said, multiply right through by 2, but you also need to flip it, right? So let's do this. So multiply by 2 and flip, right? So when you multiply by 2 and flip, what are you going to get? On the left side, on the right side of the equation, you're going to have what? 4 NH3 gas. And then on the, oh, I said right side. I meant left side. No, on the right side. What will you have? 2N2 gas plus 6H2 gas. Now, my question to you is, what effect would those two things have on the delta H value? I'm sorry?
The opposite sign and you multiply it by 2.
Exactly. So you're going to put a minus sign in front of it and multiply by 2. So minus 2 times whatever this is, 91.8 kilojoules, which will be minus itself, right? So let me work that out now. So that would be 91.8 times 2. So that would be rounded off to 3 sig figs. That would be 184 kilojoules. All right. Okay. What next? Now that we have multiplied that by 2, what would be your next step? Let me give you another hint.
Oh, the first equation would need to be multiplied by 2.
Okay,
Since there's a reactant on both sides, you don't need to.
I'm sorry?
I was saying since the NO is a reactant on the right side both times, you don't need to flip it.
Exactly. So what happens when you multiply this equation by 2? What will you get? What would be the resulting equation?
2N2 gas.
N2 gas
Plus 2O2
plus 2O2 gas,
and 4NO gas.
for NO gas on the right side. Okay. And what would be the effect on the delta H value here?
Just times it by 2.
Times what by 2?
Negative.
Minus 180.5 kilojoules. Okay, so let's work that out. So 180.5 times 2 gives you 361.0 kilojoules. All right, very good. What next? Do I need to give you another hint? What next would be your next step?
C by 3.
Very good, because you have 6 water molecules here, you have 2 here, so you're correct. Multiply this one by 3. So when you multiply that by 3, what do you get? 6H2 gas plus 3O2 gas plus, oh not plus, I'm sorry, and then the arrow, and then on the Right side, you're going to have what?
H2.
6H2O gas. So what would be the delta H value for that reaction?
Negative 3.6 times 3.
Exactly. So 3 times minus 483.6 kilojoules. Let's see what that gives. So 483.6 negative times 3. And according to my calculation, this works out. I have to round this off to 4 sig figs. So that will be minus 1451 kilojoules. All right. What's the next step?
Just see what cancels.
Right.
off
So
the equation.
in adding them together. Okay. So you're right. You're going to see what cancels out. So what would cancel out?
The 2 and 2 from the first and second equation.
Okay. Very good. What else?
The 6H2 from the first and third.
Very good. Anything else?
Would the O2 cancel partially? Or
No.
Would they? Oh, no, they'd add together because
They're on the same side.
yeah, because they're
So that means you'll add them together instead of canceling them out, right? So there's nothing else to cancel out. So you write on what's left, which would be 4NH3 gas plus 5O2 gas on the left side, and then on the right side, 4NO gas here, plus 6H2O gas. So what would be the resulting delta H value? The sum of these that we just calculated over there. So 184. Oh, I keep forgetting to put a negative sign here. That's positive, but that's negative. So 184 minus 361.0, and then minus 1451. And according to my calculation, and please correct me if I'm wrong again, but I got, now in this case, I have to round off to 0 decimal places, which means that delta H here would be equal to minus 163 kilojoules. And that's how that would be done. All right. Any questions about this one? Any questions?
I don't.
Oh, you got something different?
Yeah,
Oh, okay, maybe I'm wrong. Please correct me.
1,628 negative.
You're right. You're right. I read this wrong. Thank you. Thank you very much. I read this wrong. I thought it was 162.8, but you're right. So that would be minus 1630 kilojoules. You're absolutely right. Okay. Any other questions about this? Any other questions? Okay, so can I clear this? All right, so let me clear this now. And if I'm not mistaken, number 10, let me see what number 10 is. Same type of problem. So I'm going to leave that for you to do on your own. Let me see number 11. Number 11, same type of problem. All right. So, oh, by the way, I don't know if I told you this, but there's another link for the rest of assignment 6, right? So let me see what, I don't think there are any more Hess's law type problems. Okay, so this is a different type of problem that we're going to discuss now. So please remember, those 2 links are for assignment 6, all right? Okay, so continuing our discussion in the PowerPoint here, what we're going to talk about is what is called the standard enthalpies of formation, because enthalpies of reactions are dependent on several things. For example, the amount of substances involved depends on other conditions like temperature and pressure and so on. So in order to keep things a bit uniform so you can make meaningful comparisons between reactions, let's say, in terms of enthalpy changes, we have to, okay, what's going on here? We have to keep things standard in terms of the conditions, temperature, pressure, and so on, right? That's because delta H here, definitionally speaking, is the enthalpy of products minus enthalpy of reactants, right? That's the definition of enthalpy. However, it is impossible to determine the enthalpy of anything by itself, right? So basically, we have to use what is called a relative scale, which means that we have to adopt standard state of substances in order to determine accurately delta H values and make comparisons. So basically, the standard state or the standard conditions that are required for measurements of delta H for reactions is that for gases, the pressure would be 1 atmosphere, and the temperature of interest would be 25 degrees Celsius, right? Now, please do not confuse these standards with STP that we discussed in chapter 5, which deals with gases. That's different. That's for gases, right? In terms of all reactions, in terms of enthalpy changes, the standard conditions would be that the pressure would be 1 atmosphere for gases, and the temperature would be 25 degrees Celsius, which is the same thing as 298 Kelvin, right? So if you measure enthalpy changes under those conditions, then the enthalpy change symbol is modified specially for standard conditions. If you see this symbol right here, delta H with a 0 or O as a superscript, that means that the delta H value that it represents was determined under standard conditions, right? For both the reactants and products, okay? And then you have another symbolism here, delta H F standard, right? That is the enthalpy of formation under standard conditions for a reaction where 1 mole of a substance is formed from its elements under their standard or in their standard states, all right? Now, this one, there are tables that have been put together for this, but let me just explain what this is talking about. In fact, here's an example, right? So let's say we're talking about determining the enthalpy of formation standard for methanol, right? Then the equation for that reaction, for the formation of methanol, is what you see here. And the way you set up the equation is that you write down the formulas for the different elements here. You set the coefficient here as 1 because you're trying to write down the equation for the formation of 1 mole of the product, right? If you set the coefficient here as 1, then you balance the rest of the equation accordingly. And you'll notice that in this particular case, you have a coefficient of half for the oxygen. And that is basically allowable because, again, you're fixated on writing the equation such that the coefficient of the product, in this case methanol, has 1. So therefore, you have to balance the equation based on that. So in some cases, you may end up with a fractional coefficient of one of the substances on the left side of the equation. So basically, the enthalpy of formation for this has been determined and is equal to minus 238.7 kilojoules under standard conditions, which would be 25 degrees Celsius and 1 atmosphere, right? And there are tables that I've said before that have been put together to give you the enthalpy of formation of different substances. But before I show you the table, which I've posted in Canvas, basically, I want to ask a question here. It says, based on what we just discussed here, right, in terms of the enthalpy of formation of 1 mole of a compound, here is a question that is being asked. What is the enthalpy of formation for an element in its standard state? And here is a hint. The reactants in this particular case would be the same as the products, right? So what do you think is the answer to that question? What would be the enthalpy of formation of elements from their standard states? It would be what? If you have a reaction where the reactants and the products are exactly the same, right? Then what would be the enthalpy change?
Would it be 0?
Exactly, right? So every element that exists under normal, well, not normal, under standard conditions, their enthalpy of formation values would be 0. And you're going to see that in the table that I'm about to show you. So let's say we go here. Let me get rid of that. And let me scroll up. And let me go here. And I'm going to go to the folder which contains your tables. And this table right here, thermodynamic data, which you'll have access to in your future test. It's a relatively large document containing 8 pages. And basically, okay, so let me explain something here. You have the different substances on the left side of the table, and you have the enthalpy of formation values next to it. These two columns here, you don't need to worry about it. For those of you who have to do Chem 2, you'll be dealing with these then, right? But for our purposes in this course, we're only focused on these values right here for these substances. And as I said before, all elements under normal standard conditions will have 0 values. So you see that is true for aluminum. To scroll down, you see that's true for arsenic. Now, well, let me continue. And then scrolling down, you see that for barium, boron, bromine, right? Notice that bromine under normal conditions, under standard conditions, is a diatomic molecule in a liquid state, right? Its value is 0 because that's a value under standard conditions. But for bromine gas, its value is this, right? 30.91. So that's the reason why I stress that you pay attention to the states, right? Because the enthalpy of formation of an element in one state will be different for another state, all right? And if you continue down and look at all the elements, you'll see that their values are 0, right? So for example, calcium, scrolling down. Now carbon, there are 2 forms of carbon. Actually, there are more than 2, but only 2 listed here. The graphite is one that has a 0 value, but the diamond, its enthalpy of formation is 1.895 kilojoules per mole. Yes, sir.
So bromine was
A liquid,
as a liquid, it has a enthalpy of 0.
enthalpy of formation of 0.
Yeah, and then its gaseous state has, those values. Is bromine, is it one of the diatomic molecules?
Oh, yes, right. Right. Remember, I told you to memorize 7 of them.
Right. Is it what's its naturally occurring state?
Br2, liquid. So it doesn't exist as a monatomic atom.
Okay, I was asking like
Right.
its naturally occurring state of matter if you were to find it.
Exactly. If you were to find it in nature or whatever, Br2. And the same is true for all the 4 elements in that group 7.
But it's most often found as a liquid naturally
Yes,
occurring?
exactly.
Okay,
Right.
and that's why we use it as its base.
Exactly.
Got it.
Right. Basically, the temperature must be 25 degrees Celsius. And well, pressure wouldn't apply to bromine because it's a liquid, but the temperature is 25 degrees Celsius. So therefore, that's the temperature, or whatever the enthalpy of formation at that temperature, that's the standard. All right. Okay. So the thing about these values here is that we can actually use these values to determine the enthalpy change for a particular reaction. So let me go back to the PowerPoint here and scroll down. Okay, basically the way we use these values is described by this equation here. It might look a bit complicated, but it's actually quite simple, right? Basically the enthalpy of a reaction, if you're going to use the values in the tables that I just showed you, the standard enthalpy of the reaction would be, this represents the sum of the enthalpy of formation of the products multiplied by their respective coefficients minus the sum of the enthalpy of formation of the reactants multiplied by their respective coefficients. And that's it, right? Whatever you get there, you're going to get delta H standard for the reaction, right? Now, you could use Hess's law, but basically, this is better and easier and less time consuming. So basically, it's the sum of the enthalpy of the products minus the sum of the enthalpy of the reactants, all right? And I think I have a couple of examples here, which would be the 2 last questions in this chapter. So the first one says, hold on 1 minute. Synthesis gas is a mixture of carbon monoxide and hydrogen that is produced or that is used to synthesize a variety of organic compounds. One reaction for producing this gas is given right here. And the question is asking for you to calculate the standard enthalpy change based on the values in the tables that I've provided for you. Okay, so let me copy. Whoops. This question here. And paste it onto this Word document. Hold on, what did I do wrong? Okay, it's not. Oh, okay. All right, so this is the equation given, and the enthalpy change is what the question is asking for. So basically, what you're going to do in order to answer this question is you're going to find the sum of the enthalpy of the products and subtract from that the sum of the enthalpy of the reactants, and you have to take into account the coefficients for the different substances, right? Now, I wish I had a double screen kind of thing here because I need to refer to the table. I may need your help. In fact, I'm going to need your help, right? If you have a device and you can pull up this table here, right? I want you to tell me, I'm going to ask you the enthalpy values for the different substances involved. But first, what I'm going to do is write down an equation for calculating delta H standard. That will be equal to 4 times the delta H of formation standard of carbon monoxide gas plus, now here we have hydrogen, which is H2 gas, which exists in nature as H2. The enthalpy of formation of that would be 0, so we don't need to look up that. So that would be 0 kilojoules per mole. All right. Now that takes care of the product side of the equation, right? And then I'm going to subtract from that the enthalpy sum of the reactants, starting with the methane, CH4, 3 times the enthalpy of formation standard of methane, CH4 gas. And I'm going to add to that 2 times the enthalpy of formation of H2O liquid. And then I'm going to add to that the enthalpy of formation of carbon dioxide. There's only one, so I don't need to multiply that by anything. CO2 gas, right? So that's basically the equation you're going to use, and you're just going to plug in the numbers for the different substances, which is what I need your help for, right? So let's start off with the carbon monoxide. Can somebody tell me what the enthalpy of formation of carbon monoxide gas is? Or maybe somebody out there in Zoom land can help me out. The column immediately after the substances.
So negative 110.
Minus 110.53, and that would be kilojoules per mole. All right. So, and this will be 0, so I'm just going to put this in parentheses like this. And then now let's deal with the other side. 3 times, okay, the enthalpy of formation of methane. Oh, I remember something. In that table, I think the very last page, they have a separate table for organic compounds. So you may want to scroll all the way down to that particular last page, all right, and tell me what the enthalpy of formation. In fact, hold on, let me see here.
It's a negative 890.
Okay, this is the last page here. And methane is this. Now, again, I have to clarify something. This is not it. This is it. For some reason, they put the enthalpy of formation in the second table for this here. This is called enthalpy of combustion, right? Which is the enthalpy change when something burns, right? But this here is the value. So that's minus 74.81, 3 times minus 74.81 kilojoules, all right? Okay, and then, let me put a big square parentheses there, and then 2 times the enthalpy of formation of H2O liquid. Again, pay attention to the state, because I believe that they have values for gas and solid as well, right? So H2O liquid, 2 times that value gives you what? Well, what the value is, I'm sorry. Delta H standard
Negative 241.82.
minus 241
41.
point, are you sure that's liquid?
Oh, no, sorry, that was gas.
Oh, that was gas? Okay, so let me, remember, you have to pay attention to the states, right? Okay, so hold on. Okay, so what's the value?
285.
Okay, so 285 point, or is that it? Oh, 83, okay, 83 kilojoules, all right? And then now, for the carbon dioxide, oh, this is negative?
Yes.
Oh, my bad, okay. And for carbon dioxide, what's the value? Gas, CO2 gas.
A negative 393.51.
Okay. And that's it. All right. That's the setup. So it's all a matter now of working out what each of these would give. So I'm going to start off with minus 110.53 times 4. So this part here gives me, and please correct me if I'm wrong, but I got 442.12 kilojoules per mole. And then I'm going to concentrate now on the other side. So 3 times minus 74.81. I got minus 224.4 kilojoules. And then I'm going to add to that 2 times minus 285.83. And for that, I got minus 571.66 kilojoules. And then for the last one, it's minus 393.51 kilojoules. Whoops, what did I do? Kilojoules. And by the way, the units are all kilojoules per mole. I should mention that, right? Kilojoules per mole. If you look at the table, you'll see that's a unit for all these values. So let me just fill these in now. Kilojoules per mole, and kilojoules per mole. All right. Okay, so it's all now a matter of adding all of this up. Scroll down. Okay, so I'm going to work out this side first. All right. So that's 224.4 minus 571.66 minus 393.51. And this part I got minus 1189.6. I have to round off to 1 decimal place because we have 1 decimal place here. And then this will be kilojoules per mole. And I'm going to subtract that from what I have here. I keep forgetting to put a negative sign. There should be a negative sign here. So this would be minus 442.12 kilojoules per mole. So okay, so the final answer I got, rounded off to one decimal place, would be 747.5 kilojoules per mole. And that's how you do that. Any questions about this one? Any questions? Now, if you understood what we did here, then the next problem on that same page here, you should be able to do, right? The only difference is, in this case, they gave you the delta H. In this case, in the first example, you're to calculate the delta H of the reaction. In this case, they gave you the delta H of the reaction, standard, and excuse me, they're asking for the standard enthalpy of formation, excuse me, for isopropyl alcohol, which is this compound here. They're asking for the enthalpy of formation of this right here, right? So I'm going to leave that for you to do, right? Basically, you have to set up the equation and then solve for the enthalpy of formation of isopropyl alcohol, all right? If you have any problems attempting this question, let me know. You can call me during office hours or, well, office hours, yes, basically, all right? And then I'm willing to help you out with that. Okay, that's pretty much it for this chapter. Now, let me go to the assignment again. Clear this here. Okay, let me see. So let me go here. Okay, so let me look at what chapter 6 addendum. Okay, so basically, what we just did is what this question is all about, or these questions, right? Go to the table and you look up the enthalpy of formation standard for each of these compounds and basically find the difference between the sum of the enthalpy of formation of the products and the sum of the enthalpy of formation of reactants, and that's it, all right? Keeping in mind, make sure you pay attention to the states because the value of the enthalpy of formation is dependent on the state. They're different, all right? So pay attention to that. And if you do that, then you should be able to do these questions, all right? So make sure you do that, those questions, and attach it to the first one before you send it in. And that's basically it for this chapter. What I'm going to do now is set up a Dropbox for this assignment. So let me go here. And assignment number 6. Okay, so let me go here. Okay, now since you have a test on Friday, I'm going to basically extend the deadline for the submission of assignment number 6. Okay, I am feeling generous. Tuesday of next week. All right, let me just do this here. So available from now. Make sure this is the right year. Yep. To Tuesday. So you have until Tuesday to submit that assignment. All right? Okay, I'm thinking, since we've completed this chapter and since you have a test coming up, I'm thinking that you may have some questions about the test. Um, you know, any area of difficulty, any problems that you want to discuss concerning the test. If not, then
Is
that
that the example test posted like there was for test one, or?
you mean like a past test?
Yeah,
Hold on, let me see. I thought I posted it, but maybe I didn't.
I was just wondering if there was one, because I haven't checked it.
Yeah, let me check just to make sure. Okay, so this is a past test answer keys. Now the test will be based on chapters 3, 4, and 5, right? So let me see this one right here. Okay. Now this, I put all the tests together on one document. That's test number 2, right? So let me see here. Okay, so that is a good practice problem here. In fact, let me download this here. Okay, so the first question I can see, yes, I can see a question like that on your test number 2. And percent yield and all that good stuff. Let me see here. Question number 2. Okay, yep, I can see question number 2 as well. That type of problem appearing. Redox, balancing redox, that's definitely going to be there. So practice balancing your redox equations. All right. Let me see here. Okay, this one is a concentration type problem. So yes, I can see that being the kind of problems. So yes, that type of question can be there. And this is another, dilution. Could be there. So I would, and concentrations. Okay. Okay, gas laws. Here's one here. So that I would look at as well. Okay, very good. Yep, I would look at these as well. Okay, so that's test number 2. This is test number 1. So I would, yes, that would be a good test number 2 here. I would review that in preparation for your test. Now, somebody's asking a question here. Okay, so somebody's asking what chapter would concentration problems would be. If I'm not mistaken, that would be chapter 4, right? Because if I remember correctly, chapter 3 deals with stoichiometry, chapter 4 deals with aqueous solutions, and chapter 5 deals with gas laws. All right. So I hope that answers your question, Miss Anwar. So yes, I would look at question number 2 from that link. Let me just see what else you can look at. Let me look at this one right here. Let's see. Okay, yep, again, redox. This one here, balancing, like going from molecular equation to ionic equation to net ionic equation. So yes, you need to look at that as well. Gas laws again. Gas laws again. Graham's law of diffusion. Graham's law of diffusion again. So again, I think this one, okay, now number 3 in this test, that would not be on your test, right? Because number 3 deals with what we just completed, right? Which is thermochemistry. So for this particular test, which is test number 2, answer key fall 18, ignore for now number 3, because number 3 is dealing with thermochemistry. Let me just go down further and see what's happening. Number 4, you should look at that. Okay, yeah, so number 4, you should look at that. So basically for this particular pass test, ignore number 3, because that is dealing with gases, not gases, I'm sorry, dealing with thermochemistry, which you're not going to be tested on. All right, so make a note of that as well. Test number 2, answer key, fall 18. Let me look at this one here. Okay, that would be a good one for you to look at as well. That too. That too. Percent yield and all that good stuff. Okay, I think this one is repeated from a previous test I showed you. So you can look at that again. This is another gas law question. This is another gas law question. Redox again. All right, so that's another one you can review. So make a note of that as well. All right. Test number 2, fall 17, answer key. I didn't publish this one, but let me check it out. And this time I somehow did this upside down. Okay, no, this one is a Chem 2-1. How did this get here? Okay, so forget that. All right, but I think I gave you enough to help you to review for the test. All right, so, and I was about to say something, but I won't say it. But anyway, yeah, so just basically review those, review all your assignments, and review the answer keys, all that good stuff, and you should be in good shape. All right? Okay, so any questions about what I just showed you, or any questions about anything concerning the upcoming test? If not, that's all I have for you today. So I'll see you Friday.
Someone has asked.
Oh, somebody.
in Chat for about STEM Club.
Oh, I just sent you guys a message for you guys in STEM Club. And I created a link for Monday because I haven't had time to look at your proposed constitution parts. I'm going to look at it today, and then what I'm going to do is put it together as one document, and then I'm going to basically publish it so that the entire club can look at it and make their comments. All right. So what I'm thinking that we'll do on Monday is discuss the comments and so on, and make modifications and so on. All right. So that's basically the plan. All right. That's an answer to the question that Miss Anwar is asking. All right. Okay. So that's pretty much it. Yes, ma'am.
Will I be able to get time and a half on Friday, or should I come in during your office hours?
Come to my office hours. All right. Yes, sir.
Few questions. So, like her, I'm also supposed to get time and a half for
Oh, okay.
tests.
Mhm.
I scheduled it in the Disability
Okay.
Resource Center for today. So I need to get.
Oh. So you want to do it today or what?
No. I just need to talk to them about changing it. So
Okay.
they'll probably send you another email.
No problem.
Today I'm about to go talk to Brandon about it.
Yeah.
And then also, I sent you an email about it, but you may have not seen it. I never received my assignment 4 or 5, and
Okay.
the grade for assignment 4 isn't put in. It's still like in Canvas is missing. I sent you scans of assignment 4 because I
Alright.
submitted it late. And then I
Yeah,
gave you my.
I think that's the reason why, because usually when I grade, I just basically grade what is in the Dropbox, but, okay.
I had to email.
So I have to grade it. So I'm going to see if I can grade it today and send it to you.
And then 4 and 5, I need like the
Answer keys?
written yes, sir. It's
Wait,
like, it's sent to me. I need my version
yeah,
sent
yeah.
to me.
Right.
And then just my grade for test 1 is still a 69.
What was the issue with your tests, number one?
So there were like 3 questions that hadn't,
Oh,
you took off
right.
a bunch of points for not showing my work when
Mhm,
I
okay.
threw away the scratch paper.
I'll deal with that today as well.
Yes, sir. And I turned, yeah, so you had me turn in the scratch paper to you with the
Yeah.
test.
Mhm. All right, no problem. Yes, ma'am.
The kind of the same issue, like assignment number 5, I haven't gotten a grade back either, or
Yes.
emailed to me.
Did you submit it in a Dropbox? What's the last name?
Nelson, I submitted to you through Canvas messaging through the PDF.
That's the reason why, yeah, because like I told him,
Okay,
I grade the Dropbox assignments first. So
And
yeah, look, but you said you emailed it to me, right?
yeah, like through the Canvas
Yeah,
messaging.
all right.
And then one assignment, I don't remember if it was 3 or 4 for me. I got like a 73 on, and I realized I forgot to name some of the compounds, which is probably the main issue, but there was also a couple of other things on there that had like half points taken off that I wasn't really sure, like I couldn't really read the handwriting. I wasn't really sure what I did wrong.
Let me see here. Oh, I still have these guys here. All right, folks, I'll be signing off now. All right. So for those of you who are in Zoom,